Good morning and a very warm welcome to today's panel discussion on developments in energy storage as part of the Energy Futures Lab Future Energy Festival here at Imperial College's Week of Science. We have 4 academics for you today from the Faculty of Engineering, and I'm going to allow them to introduce each of themselves in some detail, and I will follow up with that, telling you a bit about my research as well. But my name is Dr. Sam Cooper, and I'm a senior lecturer in the Dyson School of Design Engineering. And I'm going to hand over first to my colleague from Mechanical Engineering, Monica, who's going to tell you a little bit about the work she does before we move on to the next colleague.
Thanks, Sam. Hello, everyone. I'm Monica Marinesko. I am a senior lecturer in mechanical engineering, and my interests lie in improving the performance of battery packs, especially for the automotive sector. So it is my personal conviction that modeling is here the key. And so what I do is I create modeling tools to help us understand what causes, on a fundamental level, what causes the limitations that we see in the current battery systems and how we can address this, both in terms of creating better battery units and in terms of creating what goes around the battery. So this is how we connect them electrically, how we manage them thermally, how we control what currents we allow to go through them. And what we see when we apply these modeling tools is that there is a significant amount of improvement that can be made before we consider new energy materials. So whenever someone asks me, when will the next battery electrodes material come about, I usually say, it doesn't matter. So these material developments usually take a very long time from innovation to commercialization, while engineering improvements in how to deal with the systems that we have for the first time ever of thousands of batteries put together in a very small volume, which also needs to be safe because people are sitting on them effectively. Engineering developments in how we put this together can bring about the same amount of improvement in terms of percentages within a much shorter time.
Brilliant.
So I'm also interested in supercapacitors. We also do work on beyond lithium-ion batteries, and I'm happy to take any questions on these areas. Thanks, Sam.
Thanks, Monica. Lovely. Okay, and next, we're going to pass over to Emile, who's going to introduce some of his research interests.
Hi, so I'm Professor Greenhalgh from the Aeronautics Department at Imperial College, and I'm also head of the Composite Centre. My research is really on the periphery of electrochemistry. What I do is I develop multifunctional materials that store electrical energy. So this is sort of an example of the type of thing we've made. So it's a carbon fiber composite, and it looks like carbon fiber. It's very stiff, very strong like carbon fiber, but we've imbued the capacity in the material to store electrical energy. So we're not embedding a battery, we're actually making the structural material itself store electrical energy. So it's a completely different way of using structural materials. And it's trying to bring together the sort of electrochemistry community and the structural materials composites community. So it's really very disparate areas that we're trying to bring together in this area. So we've been developing this for quite a while. We've done it with supercapacitors. We're also looking at batteries. And there's lots of big challenges with this, but the rewards with this material is that you suddenly would have huge improvements in weight and volume of the of sort of future aircraft, future cars. So to give you an example, we've calculated that if you use our material instead of batteries in a future aircraft, like a air taxi, something like that, we found that we double the range of the aircraft by taking the batteries out and turning the structure into our material. So it has potentially big improvements it could give. And it's really opening the door for a completely new way of using materials. You suddenly have a material that can do two very different things at once. So from an engineering perspective, it's really exciting thinking about how we can design with these new types of materials. But the challenges we have are quite large. How we model these materials, how we design with them, how we can make them safe, how they can cope with damage. I always get asked about lightning strike. What happens if someone hits the aircraft wing with lightning? What's that going to do to the storage of energy? So I'm very happy to answer questions on that area. Thanks.
Emile, I feel like you've teased us there. What does happen if you get struck with lightning?
Well, we've not hit it with lightning yet, but we have hit it with nails and things like that, and it's quite benign actually. It doesn't blow up or anything, which is nice.
Great. Not blowing up is one of the key properties, I think, for aerospace materials. Fantastic. Thank you so much, Emile. Chile, over to you.
Hello, my name is Chile Song. I'm a senior lecturer in chemical engineering department. So my main research interests are focused on the developing membrane materials, membrane technology for electrochemical energy conversion and storage. So as you know, the commercial lithium-ion batteries, they have been developed for larger scale applications for transport, for grid scale storage. But there's the alternative technology called redox flow batteries. So these are the giant batteries. So you can make larger scale batteries. So it's different from the conventional lithium-ion batteries. So the electrolyte can be stored outside the cell. So you can store large volume of the electrolyte to increase the energy density of the batteries. And also you can scale up the stack. So these are the new generation of batteries that are suitable for grid scale energy storage. So one of the big challenges in these batteries is that you are traditionally they're using very expensive materials like vanadium and lithium. So we're developing alternative materials like hydrocarbon membranes to replace these expensive materials, and also to integrate the low-cost electrolyte and low-cost membranes and electrodes. There's a lot of components that can be developed using latest material technology. So we're also actually looking at application of the membranes in some other, electrochemical process. For example, hydrogen production in new generation hydrogen production. For example, in electrolysis, you want to develop some low-cost technology. For example, anion change membrane water electrolysis. So one of the challenges we need to develop a robust anion change membranes. So currently the commercially available membranes cannot meet the demand. So this other area we're looking at is to focus on the membrane technologies, the materials, and also integration with the systems, as highlighted by Monica. So I think the modeling of this process is also critical. So since I'm in the chemical engineering department, we actually also have some other academics working on thermal energy storage, and a thermochemical process. So I'm happy to answer these questions as well.
Brilliant. Thank you so much, Chile. I think one of the interesting aspects about academia is that people very often don't have a clear vision of what it is that academics actually do with their daily job. And actually that can be true even between academics. Perhaps you're not even sure what each other do. One of the hallmarks, I think, is constantly trying to balance between developing your fundamental skills, whether this is some experimental techniques that you are a real master of, and translating those skills up to some kind of technologically relevant thing that a company or a government might be interested in supporting research in. And so for Monica, Emile, Chile, and myself, you are always in this tension of developing fundamental skills, experiments, simulations, machine learning, and saying, how could this be really applied in the real world to make a difference? As you've already seen, Monica, Emile, and Chile all work on energy storage devices, but these are very different perspectives on energy storage devices, and also very different devices. So I'm going to talk a little bit now about my own angle on this, my own perspective, which is that I currently focus on simulation, a little bit like Monica, so simulating energy storage devices, but from the micro scale. So you can see behind me here, I've now shrunk myself down to the nanoscale, and I'm actually inside a battery electrode. and I principally work on simulations around transport processes inside the micrometer scale. So that's 1,000th of a millimeter inside the porous battery electrodes themselves. So trying to understand what's the relationship between their shape and the actual performance of the cell. How quickly does it charge? How much energy can you store? And more recently, perhaps in the last 4 years, I've been taking advantage of some of the extraordinary gains in machine learning that companies like Facebook and Google have developed to identify pictures of cats. I've been using those same extraordinarily powerful algorithms to understand, learn, and optimize microstructural data to try and design better batteries. And that's what my group have been principally focusing on. But just like Monica, Emile, and Chile, I of course actually work on quite a wide range of activities and have PhD students sometimes focusing on grid scale storage, sometimes thinking about materials characterization experiments. And so it depends which meeting you're at as to which hat you wear on the top of your stack. So for today's discussion, we want it to be as interactive as possible. We don't want to just lecture to you. That's what we do in the rest of our job. So we would really thoroughly welcome and encourage as many questions as possible. Please make them challenging. We will do our very best to offer you our sincere opinion and perspective. Many of the aspects of the near future of energy storage are yet to be determined, and I think that's why it's such an exciting time in this area. So please submit your questions to the Q&A box on the right-hand side of the screen. This session is being recorded and will be made available through the Energy Futures Lab YouTube channel in the near future. So if you would not like your name to be published with your question, then you can of course submit it anonymously. And we will do our very best to keep this event just to 1 hour, which gives us 46 more minutes for your entertainment delight. I think having now got a feeling of what each of the 4 of us do, I think I'm going to dive in just to start a question, just while I give you guys, the audience, the chance to think of your most controversial questions. And just start by framing this discussion around energy storage, around the most popular energy storage technology today. And of course, that's hydropower, which is not what any of the speakers thought I was going to say. Almost all energy that we store in the grid is stored still today by pumping water uphill, which is not what any of us work on. We are much more interested in electrochemical devices. And the key thing to understand why we work on something rather different from that is that not every joule, which is of course the unit of energy, is worth the same amount. Okay, and a joule that you have to have a mountain storing some water behind it and access quite slowly is worth less than a joule that you can store inside a mobile phone or a moving vehicle and access almost immediately. Those joules are worth rather more. And so we are thinking about joules that you can access quickly or that you can access perhaps conveniently because they can be wrapped in a smaller package. Hard to put a hydroelectric dam in a moving vehicle or a mobile phone. So with that in mind, of course, lithium-ion batteries are the current most discussed energy storage technology. They're an electrochemical energy storage technology. And they are what has empowered the modern world. They, invented sort of only 20 or 30 years ago. And they recently won the Nobel Prize, or 3 famous scientists recently won the Nobel Prize for their creation. And they have garnered a great deal of attention because they have very high energy and power densities. They're able to store a lot of energy in a small space and charge up and discharge reasonably quickly. But of course, as you've already heard, there are alternatives to lithium-ion batteries, or certainly to the specific types of lithium-ion batteries we have today. So what I'd like each of our panelists to offer some opinions on is what are, in their minds, the most important in terms of potential impact, the most important alternatives, and are they relevant to the whole market, or is it just a particular niche that this particular alternative that they want to talk about is going to be really relevant and impactful to? So perhaps we can go back to Monica again and hear her thoughts on this question.
Thanks, Sam. Tough question. So in terms of the 2 interesting alternatives to lithium-ion batteries, for to my mind, are the redox flow cells for static energy storage, and that is simply because of the decoupling between the power and energy that they are able to give. So then,
can you explain what that means?
So normally within a closed system, in order to increase its energy density, we change the internal structure in ways that it means it has a lower power density. And I only talk about densities because we are only interested in energy or power per unit mass or per unit volume. Of course, we can always make the system bigger and then get more energy or more power from it. Now, redox flow cells, because they are reservoirs of pumping fluid that then reacts through this membrane that Chile explained, do not have this trade-off that you have to choose between one or the other as you do in batteries. And because they work on similar electrochemistry principles and microfluidics principles that are seen in other systems, I think we are closer to understanding enough about them so that we have relevant systems for energy storage. And then the other interesting alternative, as that has been, going around and discussed, is the fuel cell, which is an energy source, really. And there, I think there's been a time, maybe 10 years ago, when it wasn't clear whether fuel cell vehicles will be first on the market in terms of adoption versus lithium-ion batteries, and lithium-ion batteries just sort of happened to edge forward faster. And probably there it's not because the system is more efficient or better from a scientific or engineering perspective, but simply because the whole infrastructure required to have this commercial system of supply, demand, and charging was easier to create for battery packs than for fuel cell cars. And so some people still think that fuel cell cars are to come, but the opposite perspective is that they may have already lost the game, not because of any scientific or engineering reasons, but simply because you need a lot of wisdom to make these systems work, and the wisdom comes from the data you have available from the application that is driving around. And there is nothing you can do in the lab to mimic quite what happens when a car drives around, and the vibrations and the changes in temperature and the driver usage, which you can't control. And so we already have huge amounts of data about how batteries perform in such systems. We don't have that data on fuel cells, and that may be enough to sort of kill the dream of fuel cell cars.
Very interesting. I think, we've seen a bit with the virus, but the same is often true with technology. If you get a small amount ahead on an exponential curve, you can really dominate a whole system. I've had some interesting conversations with Michael Leibrick, who's the founder of Bloomberg New Energy Finance, who is very interested in hydrogen, but is very skeptical about its potential for powering vehicles. And some of his, I think, very compelling points around this involve the fact that, for one, I think a lot of people aren't necessarily aware that as of today, essentially all hydrogen, nearly all hydrogen, is of course a fossil fuel. It's recovered from natural gas through a sort of chemical process. So it doesn't really solve the problem that we feel we most pressingly have. Although, of course, it does solve some of the local emissions problems, but not the global emissions. But another point, which I have only become aware of more recently, is that we need hydrogen for things like fertilizer production and concrete and potentially steel in huge quantities that we are currently already struggling to provide in a sustainable fashion. The idea of using it then to power a vehicle, as Toyota once hoped everyone would, seems some way off. And as Monica said, perhaps it's now some way off in a way that means it will always be too far off, because batteries have so solidified their place in that market, or that's certainly how it appears. Emile, would you like to come in on that point?
Yeah, my perspective on sort of future where things are going is that it kind of worries me that batteries are getting higher and higher energy densities, and we're cramming more energy into smaller and smaller volumes. And coming from an aerospace background, we're very nervous about high concentrations of energy like that. So our perspective is that by using a material that does two things simultaneously, multifunctional materials, you don't need as much energy to propel your car or to drive your aircraft. So at the moment, I think some of the cars that are coming out at the moment, 25% of the weight of the car is the batteries. So you're spending a large proportion of that energy that you are using to just move the batteries around. So we've explored the idea of making the body of the car, the boot, lid and things like that out of a multifunctional material. And that means you don't need to achieve these really high energy densities that everyone is chasing in the electrochemistry community. You can get that range by having relatively modest levels of energy density, and that then has implications on the safety and longevity aspects, because you're not having to cram energy into small volumes, which means that from the point of view of fire, damage to the structure, it's not going to be a sort of catastrophic event. The heat can escape fairly easily if there's a damage to the structure, for instance. So from my perspective, and I work very much on the periphery of electrochemistry. My background is structural composites, so I do a lot of work on aircraft structures, damage to aircraft structures. And about 15 years ago, sort of moved into this idea of a multifunctional material. And this concept of material doing two things simultaneously, I think, is really exciting. If you can have a material that does that, you suddenly have really amazing things that you could try and design with that. We don't have the framework as engineers at the moment to design with a material that does two things simultaneously. So I'd really like to sort of hear what people's ideas as to how we could utilize those. So that's kind of how I see things going with electrochemistry, and it's completely changing the direction in which how we use energy storage materials.
Emile, could I ask a question around your structural materials, which is that you're probably aware that both Tesla with their sort of new big fat biscuit tin cells, as well as BYD with their blade cells, are going from a battery which they've designed and making it into a more structural component, whereas you're starting from a structural component and making it into a battery, or that's my simplified sort of summary of it. Aligned with what Monica was saying around, batteries sort of gobbling up the market in a way that perhaps fuel cells may not be able to catch up from. How do you feel about the tension between your approach of starting from the composites and working towards the cell versus the Tesla and BYD approach?
I mean, the sort of Tesla approach, they've spoken about what they call structural batteries, but it's still using two parts of a component. There's a battery, which isn't really carrying mechanical load. It's just acting in a way which moves the load-bearing members apart. And it's like a sandwich structure. It's basically using the battery to move the load-bearing material apart such that it's really good in bending. So it's something that we've been using in aerospace for decades. They're very lightweight structures. They're good at bending and compression, but you still have the battery in there, which is not carrying mechanical load. And our attraction to using this idea of multifunctional materials is that carbon is the common element in electrochemical cells and in structural materials. Both of these devices or structures use carbon. We use carbon fibers because they're very strong and stiff. Use carbon in electrochemistry because it's very good at intercalating ions and things like that. And we sort of saw that as a really nice synergy that we could exploit. Similarly, batteries are laminated structures, and what we use in aerospace composites are laminated structures. So those sort of synergies sort of attracted us to the idea of trying to make a multifunctional material out of this. And that's kind of where we've gone with this.
Nice, thanks, Emile. I think just on that, one of my sort of favorite battery facts, which I only became aware of a few years ago, is that about 30% of the mass of a typical battery is carbon, which is quite surprising because, of course, a lot of the discussion about a lithium-ion battery is focused on lithium or cobalt, when really only about 1 or 2% of a battery is lithium. That doesn't mean that that's solved that problem. Lithium's still quite hard to get hold of, but it is interesting to think. Chile, you're coming at it from a very different length scale, the biggest length scale we've got. What are your thoughts for alternatives to lithium ion and which sectors they might be very important for?
I think we have to consider many industrial process. For example, there are actually alternative big scale energy storage facility like compressed air energy storage. So you compress air, then you can expand that, through a turbine. So this kind of reversible energy storage process is currently being developed by many countries, and especially I know that in China they're developing 100 megawatt scale compressed air energy storage giant. You can consider it's kind of like a giant energy storage facility. And then there are also some other facility. I think the alternative battery chemistry like sodium sulfur, or as Monica said, redox flow batteries. There are also alternative new chemistries being developed. So potentially they can, lead to relatively lower cost compared to because right now I think also the cost is also one big issue, because the lithium-ion battery has been really established with the mature manufacturing, the production line. So many of these big energy storage facility like compressed air energy storage or large megawatt scale flow batteries require significant capital cost, the early stage investment to make the big facility. So this is one of the big challenges. How could we decrease the capital cost and also the operational cost of these large scale energy storage facilities?
So we've seen that again, unfortunately, Tesla, not to use the same company every time, but Tesla have set up a very large lithium ion based energy storage facility in southern Australia. Chile, why do you think that RFBs are lagging behind a little bit, and where do you think they're going to break through? Where do you think they're going to have their sort of first major success from a sort of market competitive perspective?
Yeah, I think there's a lot. Generally, I think the lithium-ion battery has, taken most of the market in the grid-scale energy storage currently. So there's a long list of planned gigafactory to be set up in Europe, including in the UK, on the lithium-ion battery plants. But I think there's a problem. There's a potential problem is regarding the safety, because the lithium-ion battery is made of flammable liquid electrolyte. So potentially, the safety hazard needs to be carefully designed and avoided. So I think the flow battery, if they develop this kind of, aqueous flow battery electrolyte, so potentially they're much safer and can be scaled up easily. But I think the problem is currently the flow battery, for example, they use expensive vanadium. So vanadium is, is of high cost. Of course, people have been developing. Some companies have been developing. They can recycle the electrolyte, for example, vanadium. But the initial investment, the cost for building a kind of like a gigawatt scale flow battery system is still very expensive. So I think for these emerging large scale grid scale energy storage facilities, I think reducing the cost and also think about maybe developing a brand new redox chemistry, for example, zinc battery or some organic molecules. So these alternative, potentially low-cost materials may actually lead to some breakthrough in this technology. I know that, for example, in the US, there's another company called Energy Storage Solutions that have been developing iron-based flow batteries. I think they have recently they have signed a big contract with another supply. So I think there's definitely space for this innovation and development in this area.
Right, absolutely. And you mentioned a company in the States developing RFB tech. There's also a company that I'm aware of called Ambri Power out of MIT, which does liquid metal batteries with a sort of molten salt interlayer, which sounds sort of rather steampunk and terrifying. But actually, of course, we have known how to have very hot liquids sitting perfectly safely in large buckets for 100 or 200 years. So that's perfectly manageable in principle. But they have also not yet managed to make a sort of inroad into the market. And I think it interestingly comes back to some of the things that Monica was saying, how you cannot sort of overstate the value of having deployed your technology. Because there was this very significant pull for portable devices, which are very high value consumer products, this meant that despite all the many imperfections of lithium-ion batteries at the time, there was still a strong market demand for them. And which means the factories got built. And when you build a factory, you learn so much. And when you build your first million cells, you learn so much. And so this notion of sort of learning rate, where the lithium-ion technology has developed so much because there was this very strong demand from the market. And if we can just find a way for any of these other technologies to have this very strong pull, then there's sort of no doubt that technologically we could get it done. It's just about trying to pair up the tech with the market niche.
Yeah, I want to add one more point. I think one of the key bottleneck is manufacturing. So, you know, for this emerging technology like compressed air energy storage or some other giant batteries, so manufacturing to demonstrate this kind of at a different scale, from this laboratory scale and also the pilot plant, pilot scale, and also the fully commercial industrial scale. So I think this kind of investment in this area is very important. Actually, I think in the UK, there's quite a lot of demonstration projects. For example, I know the Highview, that collaborate with University of Birmingham, developed the compressed air energy storage. They have a big plant demonstrating the technology. So this kind of demonstration and also manufacturing is also very important to especially for emerging for future technologies to be deployed at a larger scale.
Absolutely. Chile and Emile both mentioned safety concerns, and I know that's a topic that Monica is also very interested in. I think we have all been made aware through the media about various sort of lithium-ion battery fires. But I'd be interested for each of your respective technologies, Chile and Emile, in terms of sustainability, which is a slightly different take, but sort of you could imagine sustainability as global safety. Are there any particular issues or strengths of your technology in that regard? Maybe going straight back to Chile.
Yes, I agree. I think this sustainability is a big concern. So, I mean, one of the concerns, for example, in the when you're recycling the lithium-ion battery, you know, currently there's several different technologies being developed. You just burn them. Alternatively, you can recycle using the chemical aging. You can recycle all the the valuable metal ions. So I think this battery cycling will be really critical. But on the other hand, we have to consider the life cycle analysis of this, from the raw material to the end of recycling. So for alternative technology, for example, in my working area, for example, flow batteries. So there's definitely concern about the sustainability of the materials. For example, in flow batteries, the electrolyte can be recycled, but then some of the key components like the electrodes, like essentially if you develop a carbon materials, how you can recycle them, and also for the membranes, for example, lithium membranes currently being mainly used in the flow batteries for vanadium flow batteries and also in fuel cells, in electrolyzers. So making lithium membranes actually can generate some byproducts that can cause pollutions to the water, like the kind of PFA, this kind of forever chemicals. So I think there's definitely a requirement, this demand to develop sustainable materials to replace this kind of lithium membranes from the environmental perspective. Yeah.
Please go ahead.
Yeah, I think this is my point. That is my point. I think we have to think about, because on the one, we don't want to have another environmental pandemic, So Absolutely. When we develop the future energy revolution, future giant energy storage facilities, we have to consider the environmental impacts of these materials. Yeah.
Yes, brilliant. I think one of the other things that we've all observed in the lithium-ion battery, I was going to say explosion, I mean rapid adoption, has been this concept of how challenging recycling can be. And I think, Chile said that the electrolyte for these RFBs can be recycled, and that is true, and I think they're a really good example where that's actually comparatively straightforward. But there is in many cases a huge gap between what can in principle be recycled and what will be recycled with a market force driving it. And I think something that people aren't necessarily aware of is that although lithium-ion batteries can contain some scarce minerals, but also some minerals with ethical issues like cobalt, which in many cases is mined in a sort of artisanal mine. So artisanal actually is a very strange word. It puts a rather romantic spin on something rather horrific, which is sort of often forced low wage or zero wage manual labor in Central and West Africa. These materials are all still inside the cell once the cell has completed its life. Nothing is lost. The battery is a closed system. What's happened, interestingly, from a chemical perspective, is the atoms have rearranged slightly, and now it no longer works as a battery, but everything's still in there. And yet, battery recycling is still somewhat in its nascence, somewhat at its early stages, and there is reason for optimism, i.e. there's no point in building a battery recycling plant until you know that there's going to be a very large number of batteries to recycle. And so it is unsurprising that the battery recycling learning curve lags behind the battery manufacturing learning curve. And these minerals have a lot of value, so they are very unlikely to just be thrown away into landfill. But we don't necessarily have guarantees. Chile mentioned LCA, or life cycle analysis. It is a famously difficult thing to do, to fully analyze convincingly from what we call cradle to grave, from beginning of life to end of use, exactly what the impact of a particular technology is going to be. It depends where you draw the bounding box of your impact. Very often you can't model the whole world. So Emile, I'm aware with your technology that we've often perhaps use resins and carbon fibers. Things are notoriously difficult to manufacture. What are your thoughts on this? Oh, sorry, to recycle. What are your thoughts on sustainability?
Yeah, well, with composites generally, so polymer composites, it's sort of recognised that their use is very sustainable because they lightweight to structure, so they reduce the amount of energy you need to use and things. So from that aspect, conventional structural polymer composites are seen as really good. But you're right, the constituents, the fibres, the matrices, the fibres are made from quite scarce pan fibers, which are then pyrolyzed at 3000 degrees centigrade. So it's very energy intensive. But there's a big drive at the moment in structural composites to look at using lignin-based carbon fibers, for instance, and using bio-derived matrices. And so we're sort of looking at that from a structural power perspective and seeing, are those fibers that are derived from lignin rather than pan, are they better from a structural power perspective? And actually they do look better because they're not as good structurally, but their microstructure is more disordered. It allows lithium ions to intercalate into the fibers easier than for the sort of high performance, high stiffness fibers that are around. And right. There's a huge industry at the moment on recycling of carbon fibers as well. So there's a lot of sort of aircraft at the end of their life, and so there's quite a large industry in how to recycle carbon fiber composites, and we're looking at using those materials as potential electrodes for our structural power materials because they've lost a little bit of the mechanical properties, but because they're more porous, they're good from an electrochemical point of view. So I think from the technology we're developing, I think there's some good opportunities there to improve their sustainability, as well as the fact that they offer huge weight savings, and that in itself is going to reduce the sort of energy impacts that they have.
So Emile, we've got lots of questions here from the audience who are fascinated by these multifunctional materials, particularly, right. and so one of the questions which I really like is if the battery dies in your structural powered car, do you have to throw all the panels away? Do you have to throw the car away?
Yeah, I mean, we're working on supercapacitors at Imperial, and those have a very long life, much more than sort of lithium-ion batteries. And so we've been exploring using those in applications where you would look having a long life for the structure. Supercapacitors don't give us much energy, but they're good for high performance, sort of high power applications. And yeah, but you're right. If your battery function of your material has deteriorated, then potentially the structure is no longer doing what you want it to do. So we are exploring chemistries, looking at making hybrids of supercapacitors and batteries that have a longer cycle life. And yeah, we're kind of aware of that as a potential issue with this technology, and there are lots of potential issues with this technology. And I think it is, yeah, we are trying to explore ways in which we can address those types of issues.
Can I ask, do the mechanical and electrochemical properties interact? If your car's fully charged, are the doors a bit stiffer?
There are, I mean, certainly on the structural batteries, there's some really interesting interactions going on. So the electrochemical performance of the material depends on the applied stress or applied strain on the material. So you've got something that can sense. You can actually use it as an actuator. So you have a very stiff, I mean, carbon fibers have stiffness of hundreds of gigapascals. And by intercalating them with lithium ions, you can actually change their shape. So you can use them as actuators. They're very slow actuators, but they're incredibly stiff actuators.
Right.
And there is a coupling between mechanical response and electrochemical response that researchers in Sweden and KTH have been able to exploit for energy harvesting. So essentially, you can deform your structure and turn that strain energy, mechanical strain energy, into electrical energy. So it's a different way of harvesting energy from mechanical load. So it's a sort of piezochemical process.
Presumably, just to be the chair about this, presumably that's a very modest amount of energy.
It is, yeah. It's quite small, but the voltages that you need are quite low compared to something like piezoelectrics, where you need very high voltages. So there's safety issues with that. So certainly we see it as a technology that could be used for energy harvesting. But you're right, there's interactions between the mechanical aspects and the electrochemical aspects, which I think are just opportunities to be exploited from a sort of engineering perspective.
Fantastic, thank you. Monica, you touched on this just at the start. We've got a great question here from Anonymous. Which component of the electrochemical device, they haven't specified which one, so I guess take your pick, has the most scope for optimization? You know, is it the electrode, the electrolyte, the membrane, the pack system? Where should we be looking here?
Yes, very good question. I think in terms of the lowest hanging fruit, it would have to be the in-between cells. So how cells are connected and thermally managed. And what we find is that if you make small changes to how you internally design, when I say cell, it's the one battery. So, you know, it would be the one cylinder that you're used to seeing maybe in some old laptops, or your one pouch cell that is in the phone. So I'll call this a cell. We see that very small changes in how the current collectors inside are connected and come to the outside through the tabs that you would connect to the other cells can make a very big difference to the amount of heat and the way you can eject heat from these cells. So it's a purely engineering design, nothing to do with electrochemistry. And it's all related to the fact that in these large battery packs, you want to minimize any gradients in temperature, because degradation is very exponentially dependent on temperature. And so you really don't want to have some part of the battery that's more degraded than others. And in order to achieve that, you need to eject heat, not just a lot of it, but also efficiently, so that you don't create these gradients or differences in temperature. And
Monica,
so
very tricky one, but could you just give the audience some idea of what degradation is in a lithium-ion battery? What does that mean? What is degrading?
So the way you would observe it, it's simply that between the same voltage limits that are imposed throughout the entire life of the battery. So, you know, you will only use it up to a certain voltage and then you stop. You get very few kilometers left. So this is what's called capacity fade. This is how you observe it. What actually happens inside is that part of your active materials become dead. And so there are parts of your battery that you can't use as well as before. And they add extra resistance And because an extra resistant adds an extra voltage drop, it stops you from using the battery. And this is, again, in a way, a philosophical question, because we always impose the same voltage limits. We don't change the voltage limits as we further use the batteries to account for this resistance that now comes from other sources than at the beginning of life. And this is the safety issue. We are very careful in these systems, not we, the industry is extremely careful to not do anything that has even the smallest risk. And so you have to work with very large error margins.
Fascinating. Chile, we've got a question here about, well, there's a sort of lead-in question, which is when are RFBs going to be rolled out? What's the actual time horizon? There's been lots of talk about them for years. When are we going to see one operating at a sensible scale, at a megawatt hour scale?
So that's a really good question. Actually, as I mentioned earlier, so I think the demonstration of this battery system at a larger scale is critical. As far as I know, Imperial College is developing some low-cost flow battery, for example, the hydrogen manganese system developed by Professor Nigel Brandon and Anthony Kusnek. So that this kind of laboratory scale, emerging type of flow battery, it can actually be readily scaled up to megawatt if we are able to to develop the relatively low-cost electrode material, combine to scale up this to a relatively larger scale stack. So this kind of requires this kind of demonstration of an upscaling of the electrochemistry from laboratory scale to pilot scale. I think this needs investment. It needs a huge amount of money from the venture capitals or from the UK government. I know that in contrast, I know that in China, so actually the Dalian Institute of Chemical Physics, there's a really big group. They have been developing these flow batteries, and also they have scaled up the flow battery to 200 megawatt. So that is at 100. That is for storage in 4 hours energy. So that is 800 megawatt hours. So this kind of giant battery is probably still not big enough compared to the gigawatt scale, lithium-ion batteries, but it shows the potential. So I think it needs, because as far as I know, the project in China, they got a lot investment and actually also the support from the government. So I think this kind of maybe kind of like a subsidized support, I don't know, may actually be quite crucial for supporting this kind of demonstration project.
Yeah, and so we've got a sort of follow-up question around that on. As you mentioned, we've got some 200 megawatt scale plants going on, but the UK, just the UK, according to Prof. Tim Green, who apparently spoke earlier on in this series, talks about just the UK requiring on the order of tens or maybe 100 gigawatt capacity for energy storage if we had a fully sort of sustainable energy production. How big a footprint, Chile, do you imagine that would require? And do you think that's one of the major concerns, or actually not something to worry about?
Yeah, I think there's alternative strategies to develop, for example, high energy density batteries, or for example, actually there are potential solutions. But for example, polysulfide flow batteries. Polysulfide has really high energy density. So the energy density is really high, so that I think the footprint will be much smaller compared to the conventional battery plant. So actually, I think there are alternative technologies that can be developed. For example, you can actually, I know that UK and also there's several companies that have been talking about the green hydrogen, offshore hydrogen, for example. So you could actually use the offshore wind to generate electricity and then store the electricity with electrolysis, and then you can convert that hydrogen to electricity back back to the grid. So I think there's a potential. You could actually use the space. As far as I know, the flow battery plant in Dalian, So it's actually built up in the center of the city. So, and also the areas, the footprint, the area of that plant is actually not that huge. So I think that maybe we have to consider a system approach for future. For example, in the UK, if we want to develop grid-scale energy storage, we have to consider this kind of distributed energy storage solutions. We have to consider a diverse range, a wide range of options, and also that those energy solution technology should meet the local demand as well. You know, for example, in Scotland, maybe the the wind power is they have really well-developed wind power. Maybe the offshore hydrogen or this may be more suitable. I don't know.
I think that brings us on to an interesting and often quite controversial topic, which is efficiency. So certainly with hydrogen, the current technology for turning wind-generated electricity into hydrogen is very, very inefficient indeed. And then turning that hydrogen back into electricity is extremely inefficient all over again, or not extremely efficient, that's unfair, but certainly not as efficient as one might imagine. But the reason that I think efficiency can be controversial is because, once again, it depends where you draw your bounding box, your imaginary experiment. And so because lithium-ion batteries now exist out in the wild, you can measure this, and you could go to your home and you can go to your smart meter and you can see, if I charge up my car and I then sell the energy back to the grid again, you can see that actually 80% efficiency round trip, that would be doing pretty well actually. And batteries are pretty good. We could ask Emile about his supercaps efficiency, and I'm sure he could give us quite an impressive number. But of course, the downside of that is you're not getting an awful lot of energy. And so you often had these trade-offs. Chile, I'm curious, we mentioned at the start, or I mentioned at the start, that not all joules are worth the same amount of money, right? A bit of energy in a car is worth rather more than a bit of energy on the grid. And so if you want to make money buying and selling energy on the grid, let's say you buy lots of energy when it's cheap at night on a windy night in the UK and no one's using the electricity, and you want to sell it in the day when the industry is using lots of machines, that would only be profitable if your efficiency drop, your thrown away electricity, which you're turning to heat, that drop is smaller than the price difference between day and night. Do you view that as one of the major obstacles for flow battery technology, efficiencies?
Yes, the efficiency, it is one critical problem, but we have to consider the scale, So, for example, if we are able to make some energy storage facility at a really large scale, so that actually may, it's kind of like that will provide a alternative solution to the problem, because of course, generating, for example, hydrogen may actually has limited efficiency. The round trip efficiency is relatively low. That means you're wasting a lot of energy, right? But if you are able to do this at really large scale, so think about the solar panel development, like the solar power. So the energy efficiency is relatively low, but if you develop this at a really large scale, then you actually can generate a complete different revolution of the energy. So renewable energy development. So in my opinion, I think energy efficiency is just one aspect. We also have to consider the overall carbon dioxide emissions. For example, in some industry, I think there's a synergy between energy storage and also the industrial process. For example, in hydrogen, in steel industry, so they need hydrogen for the direct reduction of iron. So in this case, if we are able to generate hydrogen using relatively low cost method, and then you actually can reduce the overall carbon dioxide emission from the whole industry. So I think we have to consider the overall system approach.
That's a very interesting point. Yeah, no, a really important point for people to be aware of. Emile, a question here around the sort of relative merits of batteries versus supercaps, and perhaps do you think that with your technology it would always be a hybrid between structural supercaps and some kind of battery pack, or do you think you could have a vehicle entirely structurally powered?
Well, we've certainly on the supercaps and batteries aspect, we see those working together. So if you're looking at some device that needs a sudden burst of power to switch on, then you exploit the supercap. And then for the sort of the steady load that you're looking for, electrical load you're looking for, then it's the battery that does that. And so we're looking at coupling structural batteries and structural supercapacitors together, working with people in Sweden to do that. And then in terms of, at the moment, we're anticipating that we could use our technology in aircraft cabins, for instance. So at the moment, when you switch on your entertainment unit on the seat back, that energy is coming from the aircraft engine. So there's loads of wiring going through the aircraft, which is heavy and it's susceptible to damage. So there's a reliability issue. So we calculated that if you make the floor panels or the seat or the panels on the walls out of structural power material and store the energy there that drives the entertainment units, the galleys, and all the lighting in the cabin, you can save per aircraft about 260 kilograms. And that amounts to, I think, about 280 tons per year of CO2 savings. So the energy levels we need to achieve are relatively low, and we're pretty much there already with those numbers. I think in terms of propulsing a large aircraft, I think we're a long way from reaching those sorts of energy levels. But we kind of see that the idea of a future airliner like a Airbus 320, the sort of thing you'd fly to Greece or Italy in, if you have a combined structural power electric aircraft, that's, I think, achievable, I would say, in the next 30 or 40 years or so. While conventional battery technology, if we tried to make that size of aircraft that was fully electric, driven by batteries, then the numbers are really scary in terms of energy levels. And I think the work I've seen has suggested that you're not going to reach those energy levels until the end of the century. So we sort of see structural power as an enabler to get to fully propulsing aircraft under electric power.
Right, that's very interesting. So always with each of these technologies, it's about finding a particular niche that's going to really be perhaps synergistic with already pre-existing technologies. Monica, perhaps just very quickly in the dying minutes, be very curious to know your perspective on what are, in terms of lithium-ion cells, the kind of thing you might put in a car. What's the next big thing that's actually going to be available in the 5 years? What piece of key difference in lithium battery technology, or automotive battery technology, I should say, what are we really going to see that's different on the market in less than 5 years?
30 seconds, yes? Nothing like that. I don't think we're going to see from the outside, from the user perspective, anything drastically different. What we are going to see is batteries that have a much improved cycle life. So I'm saying here you can use them for, a lot longer. That will maybe not change the initial purchase price, but if you know that you can use it for double the time, the number of years, then automatically per usage, it will make electric vehicles much cheaper.
Brilliant. I think it's really important for people's expectations to see, why isn't technology changing? It really is, but perhaps not in such an obvious way. Okay, right. Well, I really hope you enjoyed our discussion this morning. I'd like to thank again our speakers, our panelists, Monica, Emile, and Chile. I've certainly had a really good time, so I hope they have too. So the Future Energy Festival continues shortly with a panel discussion on the power of sustainable fuels, so rather different perspective, but a lot of overlap conceptually, with guests including academics from across Imperial College, Dr. Ifan Stevens, Professor Jason Hallett, Dr. Anna Hankin, and Dr. Reshma Rao, and of course there'll be a Q&A as well. You can find the full details of all the Future Energy Festival events on the Energy Futures Lab website, and the details will be put up on the screen shortly. So thank you again to all the panelists. Thank you to the attendees for your fantastic questions, and I hope you've enjoyed the session. Goodbye.